So last time we talked about areas, started talking about that, and today it's the second part of that lecture. So I will recap a few things and go on more depth here. So basically we will look at the pseudocode of all of these phases. I hope that makes things clearer. And afterwards we will look at elasticity, which is in the context of cloud computing. Very important. So again, to remind you, those are the three tasks of Aries. So the first is the analysis phase, and the purpose is to reconstruct DPT and TT, so the dirty page table, the list of pages that are possibly dirty, so are the newer version than the one on disk. And the transaction table is a list of the ongoing transactions, so transactions that didn't commit yet. The semantics of this table is really, it must only contain ongoing transactions, the one that haven't committed yet. If a transaction commits, it's removed from that table. And these structures we reconstruct during the analysis phase, reading the log from the beginning till the end. If there's no no checkpoint from the beginning till the end. That's one task, reconstructing those. And then the second is to compute the min dirty page LSN. That is the minimum of all of the LSNs available in the dirty page table. In other words, that's the earliest possible point in time where a log record might have dirtied a page. Led to a page becoming dirty, and that dirty page now isn't available in the store. So that is the point in time where we have to start the redo phase. That's very important here. So in the second phase, in the redo phase, we repeat all actions. So without checkpoints, this means starting from the beginning of the log, reading forward till the end, you make sure that each and every page in the store no, let's phrase it the other way around. Every log record you find in the log was actually applied to the pages in the store. You make sure that none of those changes that are recorded in the log got lost. They all have been applied. They were all applied to the store. So we repeat all actions, and it's important here. It's a repeating history paradigm. So no matter whether transactions lose or win, in other words, whether they commit or not for whatever reason, everything is repeated. You don't make a distinction in the redo phase, and that's called repeating history. And then there's a third phase. There you read the log backwards, and you only consider the log records from loser transactions. Yeah? You selectively go backwards. You see that in the algorithm in a moment how that works, and only undo the actions from loser transactions. Once you did that, undid all actions from loser transactions, you're done, and your database is back in a consistent state, meaning all the changes from winner transactions now found their way into the store. All the changes possibly done from loser transactions are removed from the store. Yeah. So, and we will, I think, checkpoints is afterwards. So we did checkpoints already a little bit in the lab, but here I wrote down the three phases again and improved the slides a bit. You can download them from our lecture system. So basically, the analysis phase, the idea is you initialize. Maybe we can do 2 runs on these algorithms. Maybe first go to the checkpoints. Maybe it's easier to understand, and we can do a single run over those. So let's first, again, I briefly explained already in the lab, what is a fuzzy checkpoint. It's a very simple idea. So this is the timeline of the operations. I repeat the slides here. And one problem here is really that the analysis starts from the beginning of the log file. So that may trigger a lot of I/O. If the log file is big, if you never remove anything from the log file, then you have a lot to do during a recovery operation. So what you want to do is something like checkpointing. The idea is here not that you don't have to read the entire file, but just the tail of the log file from the last valid checkpoint. And what is a checkpoint? That's simply the state of the dirty page table and the transaction table at that point in time. So you just keep the list of pages that were dirty and the transactions that were running. And with that, you don't have to read all of this stuff anymore. Yes? You save all the I/O in the analysis phase for doing that. So during normal operation, database system writes out these checkpoints in order to speed up a possible recovery, so a possible a necessary analysis phase later on. And we also saw that in the lab. So the fuzzy checkpointing can operate as follows. Actually, it writes out two checkpoints. The first is a marker that's called the begin checkpoint that marks the version of the checkpoint. So if you write a begin checkpoint, that's just saying, okay, now there's an end checkpoint about to appear in the log, and the end checkpoint will contain the DPT and the TT. However, in between, there may be other records. Yeah? So the database system still keeps on running, and other ongoing transactions, concurrent transactions may write, update, log records, commit, whatever log records in between the begin and the end checkpoint. So you write the begin checkpoint to mark the point in time, then you write the end checkpoint, and here you actually store in the log DPT and TT as of this time, as of this point in time. So everything in between is not considered yet in DPT and TT. And that's very important when you do recovery and read the checkpoint. So we had that in the lab already. So you go back to the last valid checkpoint, and you do that, the system does that by keeping on stable storage a little file that points to the last valid checkpoint. Yeah? It points to, for instance, this point in time. And now to make use of the checkpoint, it's important that you first find the end checkpoint here. You initialize your main memory versions of DPT and TT with whatever you find here, but then you have to start processing from the begin checkpoint to make sure that everything in between is also considered. Yeah, and then you keep on processing until the end. Yeah, so major effect here is saving I/O. And yeah, we will look at that in the pseudocode now. We will see that already when you do the analysis phase. We did that in the lab already, but here again in more detail. So what I just explained is, okay, you read the most recent checkpoint, that's this one. You initialize TT and DPT tables, that's what I just explained. Then you start reading from the begin checkpoint, and then you inspect, you run a loop. Yeah? So for each log record you find, you check the type. If it's a commit log record, well, yeah, then you don't have to do anything. Commit doesn't mean there's no change involved in a commit record. It's just meaning, okay, the transaction finished, it committed, so I can remove it from the transaction table. That's all that happens. Yeah? So commit means remove it from the transaction table. Looks a little bit like pi in the font here, right? But it's transaction table, TT, what I mean here. So if it's a different type of record, that's the else branch, I check whether I have an entry for this log record. Yeah? So the transaction, so the log record dot transaction ID, basically, I check whether that is available in my transaction table. If not, this means I see the first log record of a new transaction. Yeah? So that transaction would have been in the transaction table if it had issued a log record before, but this seems to be the first log record of that particular transaction, so I will add a new entry into my transaction table, meaning, aha, there's a new ongoing transaction that's running, so I make an entry in the transaction table. Yeah, then I also set the last LSN in the table accordingly, and I have to make sure that the page mentioned in the log record, I have to check, is it already in my dirty page table? If not, then it means, that page now becomes dirty, possibly due through the change done by that log record. Yeah? So basically what this is saying is I maintain the status of the transaction table and the dirty page table. That's what I'm doing here in the analysis phase. Yeah? And recall what the semantics of the analysis phase is. It's not changing anything in the store. It's just trying to get the most recent version of the dirty page table and the transaction table. Yeah? And you see it here. It's just maintaining those tables. Here it's removing an entry. Here it's, okay, updating an LSN or possibly inserting something into the dirty page table. That's all what happens. Yeah, and when you're done with that, so when you're done processing the log, you have the DPT and TT in the version as they existed at the time of the crash. Then you do this trick, not a trick, you compute the smallest log sequence number. Again, that's the earliest log record that might have dirtied a page. and you return these three structures, so the TT, DPT, and the min dirty page LSM. That is what the analysis algorithm is doing. Then comes the second phase, that's the redo phase, and that depends on the dirty page table, but not on the transaction table. I need the dirty page table, and I could also write down the min dirty page LSN, of course, here it's in the comment, so that's also a parameter to the redo phase. So that's a starting point for doing the redo. Again, I run a big loop and say, okay, for each log record I find, I now make this, I rewrote it to the old version a little bit. I hope this is correct. I believe it's correct. I double checked it in the morning. But basically, what happens here is I do certain checks to understand whether I have to reapply the log record I have in my hands. Yeah, I want to avoid reapplying this, and in particular, I want to avoid loading data from the store and changing data in the store. I want to avoid that at all costs because that's expensive. So the first check I do is, well, okay, I have a log record. Is that even contained in my dirty page table? If it's not contained, there cannot be a problem. No way, because it would have been in DPT. So if it's not contained in my dirty page table, well, that's it. I continue and look at the next log record. If it's contained, so I continue here, so then, yeah, I rewrote it because I recently saw a nice video on YouTube. So typically when you do things like that, you have these long ifs and else nestings, yeah, and then it's very hard to read. Yeah, and there was an interesting video on YouTube I saw, and I really buy the story saying, no, write it more flat, make it flat, yeah, and really write it like, if a condition is not fulfilled, you return or you continue. And this is somehow often easier to read, and that's what I'm doing here. So it's not that such a nested structure, which is harder to read. Okay, so if it's in your dirty page table, that's basically the case here, then you check whether the log sequence number of the log record you're looking at is smaller, strictly smaller than the rec LSN you find in your dirty page table. In other words, you want to find out whether the log sequence number you have in your hands was already is non-problematic. Yeah? So the dirty page table gives you the information, okay, this rec LSN, that's the first log sequence number that might have dirtied the page. If your log record has a log sequence number that's older, in other words, strictly smaller, well, you don't have to do anything because you know the dirty page already has that version applied. Yeah, you see that? It's okay, it's an older version, so again, you can continue. All fine. So if this is false, however, then you may have to possibly apply this thing, and only then you look at you get the page from the database buffer. Yeah, so you load the page, and now you check the page LSN. Again, recall that this is for each page, yeah, on the page header, you keep the LSN. We had that in the examples before. That's the version you find in that page. That's the version of the page, basically. And whenever you apply a change to a page, you change that version in the header and make sure it gets written to disk. So basically what I'm checking here, okay, what's the version of the page? Yeah, and if that's smaller than the LSN I have in my hands, if it's equal, I mean, then it's the same thing would mean, okay, the log record I'm looking at was already applied. But if it's strictly smaller, this means, okay, the page is in an older version. Yeah, so I have to really apply the redo information of that log record. Yeah, that's the check I'm doing. And then it's important that you do this transactionally. So what you want to do is you apply the change in the actual data on the page, and you also change the version number in a transactional way, in an atomic way. Yeah, if you only change the version number, but not the data, that may be trouble. If you just change the data without increasing the version number, that may be trouble. In particular, if you're using logical redos. Yeah? For physical redos, it's not so bad. If you have after images, yeah, if you apply an after image and you apply the same after image again, that's okay. Yeah, but if it's a logical redo information, same holds for undo, by the way, then you may be in trouble. So it's really important that this is done transactionally in the general case. Yeah, is that okay? Any questions here? That's the redo algorithm. Good, and then comes undo. We did that in the lab, kind of, but algorithmically, I didn't show that yet. So basically, what you do is you initialize that, okay, again with a lock. You read it backwards, the lock then in the undo phase. And you need the transaction table at the point in time of the crash. So that's a list of loser transactions. And basically, you can do that through a heap. So the heap gives you the next log record to look at during undo. So basically, you process the log backwards, but however, only look at the log records belonging to loser transactions. You don't have to process each and every transaction. Now you hop from loser log record to a loser log record, yeah, till the heap is empty. So basically, you always draw the next element from the heap. Yeah, so that's basically the youngest log record belonging to any loser transaction. You remove that, read that entry from the log file, and yeah, then you check again for the type. So if it's a compensation log record, you have to make sure that you hop further, that you make another entry to the heap if there's a undo next LSN. If not, you can remove the transaction from the transaction table because then you're done undoing that transaction. If it's a normal log record, you again write a compensation log record as explained last time. So again, the compensation log record is an artificial record written during undo. It's not written during normal operation, it's just written during the undo phase of Aries. So you write out the log record, and then you apply the undo action described in that log record to the DB store, to the database store, and then you hop again to the next log record to undo for that operation. Yeah, the interesting question then is, okay, what happens if the system crashes? So as I told you, we want to have a system that so you run the database system and during normal operation, and then you crash, yeah, then you do the recovery, and then it's a normal operation, you crash, do the recovery. But what we want to have with Aries, and that's actually works, is even while recovering, the system should be able to recover. So you might have a crash during recovery. Why not? Yeah, and even in that situation, the system should be able to recover. Yeah, so think about what happens if the system crashes at this point in time. So as marked with the red line. So basically, you appended a compensation log record to the log file, but you didn't apply the undo action as described in the log record to the database store. So basically this means, yeah, what does it mean? You explain me. Yeah? Yeah.
It's in the log, but the action didn't actually happen, so it's a fake, it's a false log, compensation log.
Yeah, no, so think about the write-ahead logging contract. That means the state of the database is given by the log and not what's in the database store. Yeah, which in the extreme case means whatever is in the database store, I really don't care. I really don't care. Everything, the truth is in the log. And that means here, if that log entry was written, yeah, was really pushed to disk, the change happened. Not on the store, but in the log. So it's okay. Yeah? That's again the log is a database. Yeah? All other structures in the database, in databases, are optimizations. Yeah? Well, what we learned about column stores, row stores, those are all optimized layouts of the log. Yeah? Because if you had to do query processing on the log, that's terrible. It's super inefficient. Yeah? So you want to have a more efficient structure. Yeah? So that's one thing. So that's in the log. So the change happened from the point of view of the log. But the change didn't happen from the point of view of the database store. So the change wasn't applied to the store. What happens when you restart the system? I mean, it wasn't undone, so you have to undo it from the store. So do you write out another compensation log record? When do you apply the change? What happens? Yeah?
Well, since we
Yes, exactly. So we will treat this compensation log record during the redo phase. I have it somewhere written here. So let's try to, yeah, don't make a difference. So if it's an update log, whether it's an update log record, a normal update log record, or a compensation log record, the stuff described in that log record is going to be redone in the redo phase. Yeah, that's very important. So once you write out this record in the undo phase, yeah, the change it describes will the next time be executed in the redo phase. And that is why we have these weird name. Yeah, when you look at what we had here, maybe I can go back in the slides to show you, to remind you of that. We had that when we introduced those redo the undo information. Yeah, that is why it is called like that. Redo the undo information, meaning here. Yeah, when the log record is executed in the redo phase, it does something to the store which semantically represents an undo information. Yeah, so what was previously, or what was intended to be done in the undo phase, yeah, you write the compensation log record and you undo the stuff from the store, is pushed to the redo phase for any further crash. Yeah, that's the idea of that algorithm. Okay, very good. So, that sounds more or less. Okay, right. Yeah. So bottom line is, it doesn't matter that you don't apply it here. So if anything goes wrong, the redo phase will try applying the stuff as long as necessary until eventually it was applied to the store. Okay, so checkpoints we talked about. There are some optimizations that may play a role in practice. So that's again the normal fuzzy checkpoint here. What you could also do is you run a background write thread. And yeah, so we alluded to that already before. So if you think about what a dirty page means, is actually, so that's a page that sits in the database buffer in a new version and wasn't written back. Yeah, so if a page is requested very often, we call that a hot page. Many transactions operate on the same page. The likelihood is high that it will never be written back. It may stay there for years, in the database buffer, will never be written back. And that implies if you crash and have to redo, yeah, you have to start from a very early point in time in the log. So again, that's a lot of I/O. You have to start very early on, like from the log record that was written 1 year ago or something like that. So that would be completely stupid. So one idea to optimize that is to have a background thread in the database buffer that regularly writes out those dirty pages. And if you do that, you increase the likelihood, well, I mean, it's clear that must happen, that the redo will start later in the log, yeah, because you make sure that the time difference, the time delta between the version on disk and the version in the buffer is minimized. Yeah, if you do that, you don't have very old pages on disk, but you always have like whatever. It could be like maybe they're at most 5 minutes old or something like that, but not 1 year or a month or something like that, which would really harm the redo phase. Yeah, so that's a typical optimization you do in these systems. Yeah, another effect you see is for short-running transactions. So basically, when you look at the undo phase, so undo, and that's important to understand. If you think about what a transaction typically does, think about the bank transfer example we used multiple times. So you have two accounts, Alice and Bob, and Alice transfers 100 euros to Bob. That's basically two update operations. Yeah, you change whatever the value of Alice's account is and then you change the value of whatever Bob's account is. Alice minus 100, Bob plus 100. So it's two update operations, two tuples are touched. Yeah, if you think about that, yeah, even in a disk-based system, how long does it take? Something like that. Yeah, can you hear it? Can you hear it? A little bit, okay. Yeah, so it's super fast. However, this this figure here, this slide suggests, oh yeah, I mean, there may be transactions that were like open and unfinished over a very long period of time. Right? Yes, so I mean, the first or the earliest point where a loser transaction started, that's basically the point in time where the undo phase will stop. Yeah, so this basically means, so this arrow basically means that at this point in time, there was a transaction still processing which started at that point in time. Yeah, and if that is whatever, again, a week, a day, a month, or something like that, the question is, how can that even happen if I just told you, I mean, come on, transactions are just a little change here, a little change there. It's on the order of micro or milliseconds. So if what you see with short-running transactions is more something like this. Yeah, very short undo phase, because you don't have to go back that far. So how can something like this happen? Yeah, assume undo phase has to go back like whatever, let's say 10 minutes. I mean, it's hard to imagine a transaction that does work for 10 minutes. How would that 10 minutes transaction? No, the unit is milliseconds, microseconds in a main memory system. Even in a disk-based system, 10 minutes for transactions, no way. There must be something wrong. But if you see something like that some of your transactions go back started like 10 minutes ago. How is that possible? Yeah? Yeah, but here it's about metadata, so maybe it goes a little bit in the right direction, yeah? So loading a video, yeah. But can you imagine a situation in an application where that may happen? I mean, in the end, there's an application sitting on top of the database system, sending those requests, sending a begin transaction, doing operations, and then eventually sending a commit, and then the transaction is committed. Yeah. How could that happen? What is slow in a database system? Is it the database? Is it the application? Is it the UI? The user input, yeah. The user is slow. So if for some reason the application is programmed like, okay, you open a screen and then the transaction is already opened on the database system, and then the user gets a coffee or gets lunch or whatever and goes back to home and then goes on holidays, afterwards he's ill and then he quits the job, so he never commits the transaction. Yeah? So that's the only situation where that may happen. And then it might be, if that leads to database problems, to talk to the application people, hey, do you really want to organize your transaction like that? Or is it more like that after you did the change, you send one transaction, including the begin? Maybe that works for the semantics of your application, sometimes not. Yeah? So that's one thing to look at. Okay, so in summary, logging actions to a persistent medium is a cornerstone for crash recovery. And as it, obviously, arrays and variants of it are the state-of-the-art method for crash recovery in disk-based systems. But variants of those can also be used for main memory systems. And we will look at some changes actually next week probably, when we look at MVCC and how MVCC changes arrays. So it's a beautiful and flexible method. It's a building block for efficient recovery and high availability. Again, important to understand its repeating history of both loser and winner transactions. You will see it all over the place in the database systems. And the interesting thing is the algorithmic ideas can be found elsewhere as well. For instance, in applications. We talked about this undo functionality or going back in the history in an arbitrary application. However, keep in mind that main memory systems can be tuned towards logical logging, yeah? And other ways of recovering. I'm not sure whether we touched that, but that's a long story. Yeah? People wrote long books on how to recover. I just showed you one algorithm, but that's the most important one you ever need to know about. Okay, with that, we will switch to the next slide set, and that is about elasticity. So elasticity is a major thing you get when you do cloud computing. So today the term cloud is overloaded. So many people use cloud as a synonym for the web. Yeah, uploaded stuff to the cloud. Yeah, they mean the internet or something like that. But originally it was invented having other goals in mind. And the major feature was elasticity. There are some other features I will explain in the following, but elasticity is really the killer feature. And this was inspired, I did the slide set 2 years ago, and at the time there was a lockdown or close to lockdown or discussing a lockdown, I don't really remember. But what we observed at the time is that there was, the schools were using, particularly in Saarland, but also all over Germany, were using platforms for teaching purposes, uploading stuff like our CMS. Yeah? And what you saw with those platforms were problems. Sorry, that's in German. Yeah? So basically, there were news all over the place. Hey, technical problems with the school system, big fuss about online school Saarland. That was a local version of that platform. So problems all over the place. Yeah? And so I really like this abbreviation of this platform. It's SH, Schleswig-Holstein, IETS Learning. So if you remove the dot, yeah, I didn't think about the domain name too much. And yeah, so and it's kind of interesting to see that because, I mean, if you look at the hyperscalers, if you look at Google, Amazon, of all of these services, they just work all over the place. They scale like crazy. It's kind of a solved problem. And many of these problems, I claim, are due to people not understanding what they're doing and completely underestimating the effects of scaling a system. So all of these systems have this problem that there may be many, many users at the same time. Yeah? So there's typically this trap you fall into, like a developer. I'm currently also developing an application with some students. And you develop on your laptop and everything is fine, performance is cool. Yeah, if it works for one user, why shouldn't it work for 10,000, right? I mean, sure, yeah? Why would I have to test that, yeah? And basically, that is what happens for most of these platforms. Yeah? If you try to scale a system to many, many users, with every order of magnitude, you will see there are new kinds of problems coming up. Yeah? And yeah, I would like to tell you a little bit about how to fix these, how to cope with those scenarios. So in terms of the agenda, we will look at this today. How do we make a system robust against software and hardware crashes? We looked at that in the context of all of these things like crash recovery, logging and redo we did, crash recovery. This we didn't do. Areas we did. Elasticity is one. It can also be used for that. But yeah, the second thing we look at today is how to scale out, how to scale a system such no matter how many users, no matter how much load, the system automatically adapts and makes sure that response times are fine. Yeah? And that is what you get when you use elastic systems. Yeah, so when you look at the schools, you see there were, and I think there still are, many problems combined. So one is poor to non-existing internet connectivity in schools. Yeah? Okay, if you can't load the pages, then you have a problem. But at the same time, from what I saw at the time, that was not the problem. Yeah? Because I sit at a good internet connection, and anyway, a web page, I mean, it's a couple of kilobytes, maybe a few megabytes, who cares? Yeah, that's like nothing. So that was not the problem. It was really the server being slow. Yeah? You could see the server being slow. But I mean, there were a couple of problems combined here. Some were missing devices for students. That's in schools a problem sometimes. Some teachers unwilling, unfit, and unable to use the technology. I still see that with my daughter. She visits high school here, and even though the students get tablets, some teachers say, no, you're not allowed to use the iPad in my class. Yeah, I write everything on the blackboard. Okay. And then there's serious decades-long underfinancing of German public schools. Yeah? So the problems existed before, and then came the pandemic. Yeah? Oops, it doesn't work. Who could have thought about that? Yeah? So yeah, that was pretty foreseeable. Yeah, I mean, the expectation that these things would work all of a sudden was insane already. Yeah? I mean, if it didn't work before, we had all these problems with school systems and digitization in schools, so why would it suddenly work in the pandemic? Yeah, there's also a missing political will to change these things. So even after the first lockdown, which happened in summer 22, so I think that was even spring 22, not much happened to fix that for after the summer holidays. So the virologists said, hey, there's going to be a second wave coming up. We better be prepared. Yeah? Still nothing really happened, yeah? Or not enough happened, even though we knew the second wave was coming. Yeah, then 6 is a federalism in Germany. So every state does things differently, in particular when it comes to schools. Every state, including Saarland, has a different school system, which has its reasons for good, but it also leads to many island solutions and problems. Basically, each state runs its own platform. And number 7, computer science and computational thinking are still not compulsory in some states. Yeah? So you learn in school, and again, my daughter currently learns about, I don't know, integrals, differentiation, and the different classes of triangles that exist, but I keep telling her every week, you will never ever use it again. Yeah? I mean, okay, if you study math and engineering, it's okay, but how many does that? 10%? Yeah, so it's kind of weird that things that are so important, like computer science, are not mandatory. Now things start to change in Saarland as well, but it's a slow process. Okay, yeah, and then teaching platforms, and that's just what we will be talking about. I mean, you see it also when you look at certain systems here on campus. Absolutely terrible, unintuitive UIs, hard to comprehend. I remember my daughter crashing into my office saying, I'm trying to upload a file, can you help me? I mean, she knows these things, she's really good in this. And I spent 10 minutes to understand how to upload the file. And then I found out how it worked. That was really, yeah. But what we will be looking at, so there are many issues. I'm not a politician. I can only technically say how to fix these things, is poor performance on all levels. Websites, then you also saw it in terms of video calls, so teachers giving classes with video calls, and there was a problem, okay, that's more related to bandwidth things and stuff, but also the problem here in Saarland was that some teachers were asked to use a dedicated video platform provided by that Saarland school platform, which didn't scale at all. Really, it was absolutely terrible. And even simple notifications didn't really work in that system. So there are many problems, but one is missing robustness and close to zero elasticity. And by elasticity, again, I really mean the system will give you a smooth user experience. It will work independent of the workload, independent of the number of users that are trying to use the system at the same time. That is a robust system. So it's not like that when everyone is hitting the system, you can't use it anymore because every page takes like a minute to load. You don't see that there are many users. It's kind of a little bit like the eye in isolation. Yeah? The eye in isolation means, okay, whatever I do as, in the system, to me it looks like I'm owning the database system. I don't see changes of concurrent transactions. And this elasticity is kind of the fifth letter in ACID, the E, saying whatever goes on in performance, I don't care. The system takes care that performance is great at all times. I don't have to worry about that. Yeah, so we will be talking about this 8b in this lecture. Okay, and so if you look at an arbitrary teaching platform, and that is a good one, I'm really happy we have the CMS. It really works well, and okay, we have some outages and server crashes and updates, yeah, but no comparison to what schools have to live with, really no comparison. Yeah? So this is a great system. Don't get me wrong, I'm really not complaining. This is great, yeah. But when you look at that, so basically in your web browser, you just see the web page. You don't see all the layers underneath, yeah, all the systems that sit underneath. So it's a large stack typically. So if you tilt it to the side and look at the application from the side, you see, okay, underneath there's actually a layer that's the actual application, that's the actual code where stuff gets implemented. Then there may be a runtime where the application is running on top of. Then there's a database system, of course, where all the data gets stored. All of this runs on an operating system. Maybe that sits in a virtual machine, like in our project. That sits on another operating system, and that sits eventually on a physical server. So there are all these layers in a computer architecture you don't have to be aware of. Yeah? So the user just sees this. Yeah? It's a little bit like, I call that you know this when you go outdoors for hiking or for biking, your outdoor gear, yeah? You dress using this onion principle. You know that? You have like 3 layers of clothes. Yeah, and make sure to combine them really well. But when someone looks at you, he only sees the rain jacket, the outside jacket. Yeah? So it's the same thing here. So what people see, that's the rain jacket. Yeah, that's the outside page displayed in the web browser. But what is all underneath, and it's important to make sure you're warm, you don't sweat, yeah, you don't freeze. Yeah? All of these things you don't see, because this happens underneath, yeah, in those layers. That's kind of a similar principle here. Okay, so when you look at those layers, basically here's some examples how that may look like. So again, here's our stack, and here I write down different systems and hardware that sits on those layers. So the teaching application, that's the actual application being developed in whatever, Python, Rust or whatever. There may be a runtime. Then there's a database system, an operating system, and so forth and so forth. And maybe there's Docker, VirtualBox, whatever, Linux. Here we actually find some hardware. Here we find some racks and electricity and some cooling. So the arrows in between those 2 layers always symbolize the network. Yeah? So it may be implemented in different ways. So it's basically can be function calls on the same machine. So the application calling the runtime, the runtime calling the database system on the same machine. It's still kind of network. It's along an arrow. I'm making a call. It can be remote procedure calls. It can be any form of network, call and response pattern, or any mix of that. Yeah? So that's communicating one layer to another layer. So in the following, we will talk about, okay, which of those layers do we manage ourselves, and which of those layers do we push to delegate to someone to manage. And one extreme is on-premise. That basically means all of these layers you manage yourself. Beginning from the data center, you keep your own data center where you buy servers and maintain them, install operating systems, maybe also have a virtualization layer, install database management systems, runtimes, and the application. All of that is what you do. So it's a classical setup, what people did like 30 years ago, even before that. That's a classical thing people did many times and not that much anymore. So you own and manage everything in this scenario. But you could do what people call hosting. So here's certain layers. So the data center and the physical servers are managed by someone else, somewhere on the internet. Maybe for legal reasons that you may want to find hosters in Germany or in Europe. Data protection regulations, things like that. So basically, you rent a physical server, and from a company, and the company cares about all of these things like security and updates for operating systems and stuff like that. And you are just responsible for managing these layers. In this example, the operating system. Could also be that they offer something like that, the physical server plus the operating system that is managed by the hosting service. This is another variant where even less is in your hands. This is called infrastructure as a service, so IaaS. Here, you rent virtual servers, which sits on some physical server, which sit in some data center somewhere. You just get a virtual instance where you can SSH into. It's somewhere on the internet, but you can do your stuff on that instance. And that's something where Amazon became famous with. There's a classical story. Amazon wanted to have responsive websites, selling books and all the other stuff, so they had to buy a lot of machines. And the machines were such that they could manage the Christmas orders. So before the weeks before Christmas were a problem for Amazon, so they had a high load on their servers. For the remaining 11 months, the servers weren't used so much. So the idea was, why not rent it to other people to use our servers? That's basically, it's one of the modern sagas how cloud computing was born. But that's how they started. So you could grab a virtual machine, even just for an hour or two, and pay like whatever, 10 cents per hour, and you can do whatever you wanted with that machine and run your stuff. But you didn't have to care about these things anymore. You didn't have to buy the machine, get offers, pay the money, install operating systems, or even care about a data center. Yeah? If you buy a machine here at uni, you have to always make sure, okay, where do we put the machine anyhow? Yeah? Another level is called platform as a service. So here, the only thing you manage is the application, but everything else is managed by the provider, whoever provides that. So including the database system, operating system, and the runtime. Yeah. So that's more extreme. And the most extreme is called software as a service. Software is a bit misleading. Actually, what's meant is application as a service, but you will only see this term when people talk about that. So basically, you rent the application. Everything is handled. It's like whenever you use a service where you just log in, or even if you type in a search in Google, it's kind of software as a service. You don't have to install Google on your machine. You can use it without logging in, even as it's kind of software as a service. Or another example is Google Docs, yeah? Google Drive. That's all software as a service, basically. Yeah. So that are the different levels you can identify, and in between there are levels you can, of course, identify if you wanted. Huh? And an analogy to explain that, I found that on the web, is pizza as a service. Assume you want to eat a pizza. Yeah? And now, with these different service level agreements I just explained, so the extreme case, you make all of that in your kitchen. Yeah? You handle all of the layers in your kitchen. That's basically the equivalent to on-premise. Now, if you just get the cheese, the toppings, tomato sauce, and the pizza dough, so in German that's Teig, yeah, pizza dough, from someone else, but everything else you handle yourself in your kitchen, that's called, that would like take and bake. Yeah? So you get the ingredients, but bake it back home in your kitchen. If the pizza is delivered, that's the equivalent to this one. Yeah? So the pizza is prepared and cooked, and all you have to do is to unpack it, get something to drink, and sit on the dining table and eat it. That is platform as a service, or pizza being delivered. And if you completely dine out, that's the equivalent of software as a service. Yeah? Not sure whether that helps you. I found the analogy quite nice. Okay. And this idea of delegating responsibilities in your software stack to someone else has many, many advantages. So in particular, for the green or rented parts, you don't need to manage software updates, security updates, which is really a pain, hardware procurement, maintenance, repair, data centers. Data centers are really expensive to run, in particular in terms of electricity for the servers, but also cooling is super expensive. You have to hire administrators, database administrators, whatever. So it's a huge check you have to pay. So renting may be more reliable and more secure and much cheaper than doing it on premise yourself. Huh? So there are two extremes you can ask yourself. Yeah? If you look at the extremes on-premise and software as a service, so if you do all of this yourself, this means you run the show and take the risks that things can go wrong. And then the question you should think about is, are you sure that you have the staff knowledge and experience to run all of this? If you have just one guy or two guys, yeah, let's say Horst and Peter, who do all of this, are you really sure they can do that, make it reliable, scale it like crazy, make sure all the security patches are applied, everything is updated? If anything breaks down in the middle of the night, on Sunday night, are they going to fix it or not? Yeah? Whereas others run the show, and here the likelihood is that you have a scaling effect. So these companies that provide that are called hyperscalers. That's the term for that. And they have thousands of people working on that. They may have thousands of people just working on the database part, thousands of people just working on virtualization. And so highly skilled teams that are available 24 hours. And if anything breaks, they will fix it. That doesn't mean that this will not break down, but the likelihood increases is that this has a much higher availability. Yeah. So you should really ask yourself when designing a stack like that, do you do something like this or do you do something like that? Yeah. And what you saw on the school platforms was something like this. Yeah, there's one more advantage, and that is this elasticity aspect I mentioned before. So here's the definition of elasticity. So the degree to which a system is able to adapt a workload to workload changes by provisioning and deprovisioning resources in an autonomic manner, such that at each point in time, the available resources match the current demand as closely as possible. Think again about the pizza example. I think that's a good analogy to explain what that means is, if you do this dine out, you're at a restaurant. So the restaurant has to take care that you don't wait too long to get your pizza served. You have the restaurant has to make decisions. How many cooks are in the kitchen at any point in time? How many waiters are there? How many tables do we prepare? So not the database tables, but the tables where you sit on to eat your pizza. So that's called provisioning. How many resources do I use at any point in time? So the software, the restaurant has to take care about that. And the same happens in computer systems. Someone has to take care about that. And you want to do that you match the demand. And that should include failover recovery and so forth, and in particular, automatic scaling. So how do you scale these systems automatically? And the hyperscalers have solutions for all of that. So basically what these layers do, and we will use that in the following, is that they have a contract. It's similar to any layered architecture. So you're on a layer xi, and it serves incoming requests from a layer above, xi plus 1. So this xi plus 1 makes requests to layer xi, and xi in turn makes requests to layer xi minus 1. And what you want to do is you want to scale to any number of incoming requests. In the end of the day, you have many problems due to having too many requests on a particular layer, and you want to make sure that you're still that you can do something. If there are many, many incoming requests, you can still handle that somehow and act upon that. And the second thing, of course, in particular, if data, there's always some data state consistency problem typically in these systems. You want to be able to handle failures, consistency issues, and so forth and so forth. In terms of terminology, these layers are also called tiers sometimes. If you see that, but that means the same thing. So if it's layer or tier, it's the same thing. And there are some problems with this kind of layered architecture visualization. One is this graphic is just a conceptual view. So this graphic on the left basically just says, well, there is a layer named X, and in principle, it is responsible for doing Y. So there is a database layer responsible for doing data management and query processing. But that may mean much more. So what is missing here is how are the boxes and arrows actually implemented? What is inside such a database box? What is inside an operating system? And how do they communicate? So that's one problem. And the second is the graphic is hiding the one-to-end relationships in between the conceptual layers and the actual instances. So if you have a data center, of course, a data center will have multiple physical servers, 4 in this example. On each physical server, you might have one operating system with multiple database systems. Here's 4 database systems. There might be virtualization layers and so forth. So you don't really see that in this graphic on the left here. It all looks like one-to-one relationships, of course, but it's one-to-n relationships typically you will see in these systems. And another problem is that it's sometimes not a clear layering at all times. So it can also be like something like this, where you see, okay, there's an application, it talks to the operating system and the file system maybe, and to the runtime talks to both operating system and the database system, and so forth and so forth. So some layers may be not only call the layer underneath, but also other layers underneath. So that may also happen in these architectures. So this graphic is really a simplification. That's important to be aware of that. Yeah, and if you look at the minimal database architecture, that's called the three-tiered architecture. That's the standard thing you will see. So many applications, many information systems that do something with the database system underneath can be explained along those lines. So basically, you have a database system, you have an application, and you have a client. Those are the three tiers or layers you can identify. And here also depict storage underneath. And yeah, then you can think about, okay, what is the round trip? So the user does something on the client layer. The client then interacts with the application, which in turn interacts with the database system, which may interact with the storage to write or read files. And yeah, that's both scenarios may happen. Returns some results to the application, which returns the results to the client, which displays those results to the user. So that's a typical round trip from user down to the store and back. Let's assume for the moment that this runs on a physical server. So let's look at some performance problems that may occur in such a world. So, I mean, you have your database application up and running, everything is fine, you have a couple of users, they are all happy, response times are fine, yeah? All is good. But then if you add more and more users, and again, as I told you, school platforms or systems managing your grades at the university also fall in that class, things may slow down and users will be complaining, oh, the system is too slow, why is that happening? So typically the reason is that you will have congestion, meaning that too many calls, and it may be on any layer. So too many calls that cannot be served fast enough anymore. So for instance, interaction congestion. The data delivery may be slowed down or stopped, or it stops completely at any of those arrows, maybe between storage and database system, maybe between database system and the application. And what you can do if you have this, the first thing is, if you are in that situation, you have to identify that this is a problem. Yeah, and then you have to remedy that. Yeah? But to identify, you can check the networking and round-trip behavior of your application. There are actually tools that allow you to do that. I think Amazon Lighthouse or something like that is helping you with that. And then check the amount of data being transferred in between those tiers. So typically what you see in database applications is that the application developers write queries that select way too much data from the database system, and that data is returned to the application and post-filtered in the application. So rather than pushing down a selection predicate, for instance, as we learned about in query optimization, there's a tendency that developers select way too much data, which of course has to be transferred, has to be processed in the application, even though that processing could have happened in the database system in the first place. Yeah? It's easy to get that wrong, and I'm also getting that wrong. I'm currently writing an application, and I also did that mistake. It's really easy. Yeah? But this may hurt once you scale out. Yeah? If it's just one or two users on the system, you don't see this stuff. But if there are thousands, this will multiply with the amount of requests and may become a problem. Yeah? So that's very important. Check the amount of data being transferred in between those tiers and try to reduce that data if possible. So basically, we reduce the I/O in between tiers. That's a very important thing here. Yeah, the other is the application may become the bottleneck. So there's congestion in the app. So database system is fine, super fast, everything. Storage is okay, no bottleneck there, but the application has a problem. What can you do? Well, of course, you use a profiler. So if you haven't used one, Profiler is a standard tool to analyze the performance bottlenecks in your program. You should really know what a profiler is if you do any programming. Google Profiler, Google for that, and there are many, many tools you can install for that. It's super helpful. So you check the CPU load, which process consumes the most CPU. Yeah? Is it the application? Is it the database system? Check the implementation, check the concrete function that has that problem. So one typical thing you see in applications is hidden square complexities. Yeah, so you write down a loop. In the loop, you call a function, and the function again does a loop based on some parameter, and then you have, boom, a squared complexity. Yeah? It's really easy to get that wrong. So try to identify bottlenecks, try to identify whether the problematic functions and rewrite them if necessary. Check memory usage, thrashing of pages, threading, locks, unnecessary waits. Yeah? Sometimes the concurrency is typically something that can also lead to problems, not only performance benefits, of course. Yeah, the database system may, of course, also be the bottleneck. Yeah? That you can check. Yeah, we touched some of those problems already in this lecture. I think I wrote down a couple of more you can check. So you check the query plans, explain. Yeah? If you write in your database shell a SQL command, just write explain in front of that, and you get the physical query plan that's used by the database system. The syntax may vary. I think sometimes you have to write explain, analyze. Some systems you just write explain, but the database system can tell you the physical query execution plan it uses. Yeah? And if you look at that and feel like it's stupid, yeah, maybe you better act upon that. Yeah? Sometimes plans are stupid, and but sometimes there's a reason for that. For instance, when an index is missing. Yeah? I think I wrote it down somewhere here. Yeah? Create suitable indexes. Yeah? Again, a problem that doesn't occur on a single machine. You're testing it for yourself. Yeah, so the query takes like whatever 100 milliseconds. Yeah, but now you have thousands of users hitting the machine at the same time, and then if you don't have the right index, you better create it. Yeah? So make sure the right indexes are created. Check default parameters. So we talked about default parameters already along the lines of Postgres. So isolation level, yeah, is read committed is the default in Postgres, which is a bad idea, which is a leftover, which is legacy. It should be serializable. Actually, we just had a database conference where there was a paper where people analyzed concurrency bugs of applications using Postgres. And they found many problems in those applications that were actually due to people not being aware that the isolation level was set to read committed and what it meant. Yeah? All of these problems could have been avoided in the first place if the default isolation level of Postgres were serializable. Completely stupid, completely unnecessary waste of time. Yeah? But yeah, so be aware when using a database system that it uses serializable as the isolation level. And buffer sizes is another story. Postgres ships by default with a very small database buffer size. You should increase that to match your memory, of course. Yeah, create suitable indexes, double check isolation levels, I mentioned that. Threading and locking behavior can be analyzed. Then next week we will look at a variant of concurrency control that comes with a couple of more hyperparameters, configuration parameters. One is garbage collection. I will explain that next week and should be checked. Yeah, how does the database lock work? How is it configured? Did you put it on a separate fast disk? Is a database lock the problem? Check it. Use physical design advisory. So physical design advisory is a tool allowing you to optimize the physical design. There's a physical configuration of a database system. So some expensive database systems come with that. For instance, Microsoft SQL Server, I think Oracle as well. That's a tool that inspects your workload and inspects your database schema and the data contained in it, and then proposes certain indexes, proposes certain partitionings, proposes even a hardware configuration to match your service level agreements. That's a very important and very helpful tool. And if in doubt, get a database consultant. Yeah? So you can do so many things, configure so many things in a database system that require a lot of experience. It's simple things that can make orders of magnitude difference in a database system. Then rather pay a couple of $1,000 for a consultant than redesigning all of your application yourself or doing stupid things. Ask someone who really knows these things. They can become really, really difficult. Okay, the storage may be the bottleneck as well on storage, but there are easy solutions for that. So again, you could also profile the I/O behavior. So how much random I/O? We talked about that at the beginning of the lecture. Random I/O may really be a killer for any system. If there's too much random I/O, that may overload the storage device, and that's a problem. Is that something you can fix in the database system? Can you somehow lower the I/O load, for instance, by providing the database system with more main memory, such that you don't have to do fewer requests to the store? You can check the data layout and the compression. That could help. And you should always worry about, could more main memory in the database system fix it? So there's an important principle that's called kill it with iron, or Kiwi principle. And it sounds a bit trivial, in particular, as we computer scientists, we want to do fancy algorithms. If there's a problem, we develop better software, a better algorithm. But in industry, that might not be the wisest choice to make. If you find out you have a problem with I/O, you first ask yourself, oh, are you using spindles? Is it really hard disks? And you have a problem with that, so why not get SSDs? Yeah, first do these things, because from the point of view of the company, that's no money. They're getting a couple of SSDs for a couple of, I don't know how much data you want to store, but that's the first thing you do. Yeah, you change the hardware, try to get better hardware, because if the problem is fixed, then no one has to touch the running system. Actually, no one has to touch the code, has to worry about algorithms that have to be tested, so that may break down things. Yeah, so it's the easiest and first thing you should always try. Okay, maybe it's a matter of having a different server or better storage hardware. Yeah? And of course, for SSDs, you can get PCI-attached SSDs. It's pretty much standard these days. Use RAID. You can use RAID with SSDs, of course. As I told you, RAID SSDs internally, even also use RAID internally, but also externally combine multiple SSDs in the RAID system. That's fine. Add more disks in SSDs. Maybe it's a matter of too few disks, in particular for random I/O. We talked about that when we discussed RAID levels. How was it with RAID 5, for instance? Yeah, you can distribute the random I/O over the different disks, of course. Yeah? And the same happens for, even for the smaller RAID levels. Not the for RAID 1, you can do that, for instance. Yeah, if you have mirroring of your disks, you can route the random I/O to distribute it over all the disks you have. That may help already. Yeah? Okay, so to fix those performance problems, we can add more resources to a physical server. Add CPUs, memory, SSDs, and disks. So basically, what you're seeing here is the entire stack runs on one machine. So the application, database system, and storage, with whatever hardware you're using, sits on one physical server. Yeah, and the first thing you can do to fix performance problems is to assign more hardware or distribute layers to separate machines. Yeah, that's what I'm showing on the next slide. So here basically you have a separate server just for storage, some storage server. You have a database server, really a physical server, and you have the application server. Yeah, and that may already help to fix those performance problems by adding more servers and assigning a server for each tier separately. Here it's one separate server per layer in this example. But of course, you can also do something like that. You say, okay, why only use one server for my application tier? I can use multiple servers. Actually, when SAP started, I don't know, 30, 40 years ago, that was one of their main tricks they played, yeah? when they developed their information systems, that the application server could be distributed across multiple servers, which helped a lot in scaling those applications. Yeah? That was a very important performance trick. And the same can be done with database systems, of course, and even with storage. For storage, typically, if you have a problem with too slow storage, you eventually look for separate storage servers and systems that give you insane performance, basically. Yeah, so they're dedicated hardware vendors that provide high-performance storage servers. Yeah, challenges with that is, and that makes it really interesting, you want to scale this up and down automatically. Yeah, so if there's a problem, you automatically add more resources or distribute your architecture across more machines. That's the cool thing you want to do. Yeah? And without interrupting operation, without fiddling with things, without losing any of the properties like being able to recover and asset and stuff like that. That makes it really difficult. And that is where these hyperscalers, cloud providers, can really be super helpful. Yeah? You want to hide that from the users. Yeah? They shouldn't know this magic. And you want to be able to cope with any problems on the way, be it hardware, software issues, consistency issues, and so forth and so forth. It should all be transparent to you. You don't see that. No? Again, like a fifth letter being added to assets, like an E. No? Yeah, so what that means is the more you are on the left, yeah, the more it's manual scaling. The more you are on the right, the more it's automatic scaling. So it depends on what you get from those hyperscalers. It could also be that you just get a virtual instance where there's no elasticity built in already. Yeah? So these hyperscalers provide many, many different services. So, but if you log into Amazon Web Services, you see there's tons of different services. It's not just getting a virtual machine, but all kinds of levels and instances you can combine freely and orchestrate. It's really insane. It's really cool. So I'm just trying to tell you, you don't get necessarily elasticity just by going to Amazon. So it depends on the service you're picking. Yeah? Some offer elasticity, others don't. Yeah? So you have to read the docs at that point in time. But the general thing you will be seeing is the further you go to the left, the more you have manual scaling. The more you go to the right, the more you have automatic scaling. So here you configure, add and remove your own servers if you have performance problems. Here you configure, add and remove rental servers. You configure, add and remove virtual servers. You configure runtime. You configure the app. So it depends on the application that you want to offer. I mean, you have to think about which kind of, how much of that architecture you want to delegate to someone else. Because it's also a money question, of course, at the end of the day. Yeah. Okay. So the technical summary of all of that is Foo as a service models are very suitable for many applications, in particular teaching platforms, but in general, any platform with many users and or heavy workloads, and in particular, a varying workload. Yeah? Sometimes few, sometimes many. You have peaks, you have lows and stuff like that. If your workload is like more or less all of the time at the same level, it's relatively easy to provision. Yeah? You get just as many servers as you need. But then if you have peaks, you have a problem. If you have fewer users and you're not making use of your hardware, which is also a problem money-wise. Yeah? So this Foo as a service model has many advantages. It may be cheaper overall. Yeah? If you look at the operating costs of all of that and make the math, it may be more reliable and secure. In particular, if you factor in how much personnel you have available and what can they actually do on your architecture, you get elasticity, yeah, if you want, from those hyperscalers, which may be super useful. And yeah, it may be that you only need few people to run huge apps. Yeah? So there's a saying now: a 14-year-old can build what 15 years ago took 100 people. To build a software that is used by many, many people, back in the old days, you had to do it on premise. You had to get a data center. You had to buy servers. You had to install all of that and manage it. Now you get just a service from Amazon. You make it elastic, and if it scales, but it still works. Yeah? So it's not if you understand how these things work, it's relatively easy to do. Yeah, disadvantages are, of course, privacy concerns. So what kind of data do you want to store? Is that personal data? Does it, if GDPR is a problem for this data, you should be careful. Yeah? So this is partially fixed by those providers, so you also can ask those platforms to get a server in the European Union, for instance, or some providers also allow you to say, hey, I guarantee the data is stored in Germany and it will never leave Germany. Yeah? So they make these kind of offers. So you have to be careful with that. In summary, we just scratched the surface here of what's possible with these architectures. So for developing real applications, it's really a great option to look at. So I sound like an Amazon salesman a little bit. But what I'm trying to tell you, it's not only Amazon. There are others, like, I don't know, in Germany it's Hetzner or something like that. Azure, Microsoft, Google Cloud, stuff like that. Yeah. And if you look at that, where those instances sit, we come to the next slide. And that is a political summary. So Foo as a service are simply different shades of data infrastructure, of infrastructure. And it's super weird that we finance streets, railways, water, gas, and electricity supply, but no digital infrastructures. It's super weird. It's already weird for search engines, if you think about that. That's weird for fiber cables for your internet connection, but it's also weird for these as-a-service architectures. To my understanding, that should be financed by the state because it's so sensitive. We are so dependent on these things. Yeah, assume Amazon breaks down all of a sudden for whatever reason, for some revolution in the US or whatever. Weird things are happening in the US. Many companies in Germany would have problems. Many. Yeah? So if you do it right, you can also migrate your cloud application quickly to another cloud provider. Yeah? That's another great thing you can do. But maybe if you didn't do it right, you have a problem and you're stuck with a cloud provider, and then it's not so easy. Yeah? Then if that provider breaks down for whatever reason, for political reasons or things that may make you unhappy, yeah, that's a problem. Yeah? So to my understanding, each country should provide and maintain this as part of its infrastructure. It's just our thinking that's in the way. Yeah? We believe that streets and railways are infrastructure, but all of this as a service is also infrastructure. Yeah? Again, the same for search engines, the same for any computational service. Yeah, and the dependency, again, on other states and companies here is insane. Yeah? So if you, again, that's what I meant with the slide before. Yeah? All of those are US companies. Yeah? You could also go to Alibaba in China. I guess Russia has a similar service. But why should you depend on scaling by using a foreign entity? That's really weird. Yeah? And if we had working services like that in Germany, the scaling aspect of building a teaching platform would be mostly a non-issue if you know what you're doing. Yeah? So many of those problems I showed you initially in this lecture are due to people trying to do it themselves, trying to install the entire stack, yeah? Keeping a server somewhere in the basement in some Duttweiler cellar. I don't know, yeah? It's really insane, yeah. That's not how you should be doing these things these days. Yeah? So, but politically, this is something that's really I'm seeing as a problem. Okay, so that much about elasticity. So please revisit the ARI stuff, revisit the major ideas of that. We will look at that in the lab, and next week we will look at concurrency control with MVCC and versioning. Yeah, see you then. Bye.